Hello, thank you for joining. I am Vinicius Ribeiro from the University of Campinas, Brazil, and today I will present our paper Less is More: Sample Selection and Label Conditioning Improve Skin Lesion Segmentation. This work is a continuation of my two previous works. The first is handling the inter-annotator agreements for automated skin lesion segmentation, and the second is my Master of Science dissertation at Unicamp. You may find the links for both of them in my personal page. Semantic segmentation is a complex task in computer vision, since in many magical tasks the boundaries of the objects of interest are fuzzy. The images may suffer from low contrast or other quality issues, and undesirable artifacts may be present. Method-specific characteristics are an extra complexity. The many segmentation methods might have different levels of granularity. The ground truths in the ISK archive dataset were generated by one of the three. In the first row, you can see a segmentation mask generated by flood fill controlled by the annotator, which generates a very granular mask. Manual polygon tracing is another method that you can see in the second row, which produces a geometric mask. Fully automated segmentation validated by a human is the last one, generating a pixelated mask. Different physicians might also diverge about which pixels of the image belong to the lesion and which doesn't. To adjust the agreement between the physicians, we use the Cohen-Kappa statistic. The advantage of the Cohen-Kappa score over simple intersection metrics is that it accounts for the possibility of the two annotators agreeing by chance. Kappa ranges from -1 to 1, where negative values represent agreements worse than chance. 0 is pure chance, and positive values correspond to better than chance. In some cases, we have such a substantial disagreement that the Cohen-Kappa score is lower than if we had a random annotation, as you can see in the first row. The two annotators don't agree even in the location of the lesion in the image. In other cases, even though the specialists agree on the location, they disagree about the area corresponding to the lesion. In the third example, in the last row, the annotators only disagree on the border pixels. We can see that they substantially agree on the core of the lesion. In this work, we characterize the divergence between the annotators. Our objective is to alleviate those divergences. Finally, we evaluate the impact of our methods in the evaluation of machine learning models. Our approach consists of data elimination with label conditioning. Sample conditioning is a pre-processing technique we can apply to our targets. By employing simple and well-known operations, sample conditioning acts like a regularizer, removing small details that might prove distracting for the models. We propose two methods, producing distinct outputs. The first is the morphological open, which removes white spots from the image. The second is the opening followed by the convex hull. By applying our conditionings, we can observe two cases. First, for a large group of images with high agreement, the conditionings work displacing the distribution towards 1. For a minority of the cases, the heavy tail of the distribution, the agreement is so low that none of the conditionings could help. Fortunately, the conditionings didn't worsen the problem. In our approach, we remove the tail of the distribution, withholding the images with Cohen-Kappa score lower than 0.5, which corresponds to 19% of our data. In our experiments, we work with the ISK archive dataset, which is the only one to provide more than one annotation for each image. For training, we select only the images with 2 or more annotations, since it's the case where the Cohen-Kappa score can be appraised. We divide our training data into 2 groups. The first containing all the samples, and the second containing only the best samples. the ones with kappa higher or equal to 0.5. For testing, we evaluate our approach in three datasets: 2,000 images randomly selected from a subsample of the IDC archive with only one annotation, the PH2 dataset with 200 images, and the Edinburgh Demo Fit with 1,300 images. During training, we randomly select one of the available ground truths for each image. Then we condition the mask and pass it through the model. During validation, we evaluate the model with all the available masks and consider the best results. For all runs, the conditioning during training and validation are the same. For each run, we select the model with the best performance during validation. For test, we only have one available ground truth, so mask selection is not a matter. To guarantee that our results are not model-specific, we employ two distinct architectures: DeepLab v3 Plus and LinkNet. The models and the training pipeline were implemented using PyTorch framework. We developed all the conditionings in Python using the scikit image library and auxiliary code in NumPy. All the code necessary to reproduce our work is available at our GitHub repository. In this figure, we have an interaction plot highlighting the effect of sample selection. In the columns, we have the conditioning during test, known, opening, and convex hull. And for each column, we have the conditioning during training. The orange lines correspond to the runs with all the samples as training datasets, and the green lines corresponds to the best samples as training datasets. The observed effect can be appreciated on the solid lines in the plot. We can see that withholding the low agreement samples systematically drives better results than when we feed the models with all the data. This result is not trivial, since we discard close to 20% of the training samples, and we do not perform selection on the evaluation phase. In deep learning, more data often presents better results, and discarding data is not the common sense. In the second figure, we present an interaction plot highlighting the effect of label conditioning for train and test phases. The format of this plot is the same as before. We have the conditionings during test, we have the conditionings during training, and we have all the three test datasets. Note that for this plot, we only consider the runs with the best samples. Surprisingly, we see that the removal of the border details during training does not reduce, on average, the performance of the models. Even though we require the details during tests, the models are still able to reconstruct the detail on inference. The improvement is particularly pertinent when the details are not relevant to the final objective. For example, when we only want the overall shape of the lesion, applying the convex hull during training and test sharply increases the results, as you can see by the third column. Note that for both plots, the results may vary according to the dataset. We ran a full factorial ANOVA, and all the factors were found significant, with tiny p-values. The main source of variation was the test set, accounting for 88% of the variation. In conclusion, we see that the segmentation ground truths for skin lesions have a substantial disagreement between annotators. Contrary to common sense, we also see that it's possible to withhold the bad samples, those with lowest agreement, and still achieve competitive results. And removing details from the segmentation mask may improve the results. The proper condition for the final objective might lead to a larger improvement than more complex models. Our design is applicable only when more than one annotation per image is present. In the future, we expect to extend our findings to single ground truth masks, increasing the applicability. Thank you for watching. Here you can find our contact information and get access to our code through this QR code. If you have any questions, do not hesitate to contact us.